Hi, Chris Good here, and this is part one of our first lecture on the experimental design and the independent measures or independent groups or between subjects t-test. Okay, so after this lecture you should understand how and when to use this type of experimental design, the independent measures, independent groups, or between subjects design. And you should be able to identify potential confounds in a design like this. You should understand how the statistical test relates to the design. You should be able to state and understand the appropriate null hypothesis. We'll get to that in this lecture. Compute the appropriate statistic to test for a significant difference between two independently sampled means. That's kind of the whole point. To make a statistical decision about your null hypothesis and to interpret it. Also, you need to generally understand and apply the statistic to the appropriate design. Okay. In class, we were talking about this nutritional supplement, ginkgo biloba. It's supposed to improve your memory, although it says on the box that those statements aren't evaluated by the FDA, so we tried to come up with a way to actually evaluate it. Does this product actually improve your memory? And the design that we came up with was an independent groups design. We also call this the between subjects design. And your textbook calls it the independent measures design. And what that means is that there's at least two groups of different people that are being exposed to different treatments. And you guys came up with the design, and it involved assigning people to either take ginkgo or to take the placebo treatment. You guys had a placebo-controlled experimental design. But there were different people taking placebo than there were taking the ginkgo. So when it's different people in the different groups, they're independent, as independent measures or between subjects. Repeated measures are when it's the same people who are exposed to the different treatments. Like if we had had people, take a memory test with nothing and then take ginkgo and then take it again, then that would be a repeated measures test because we're repeating the measure and we're looking for differences within the same group of people, not between groups of different people. So we call that a within subjects or repeated measures design. And we're going to come back to that design in a later lecture series. So you guys assigned people to take a placebo in the control group as a way of preventing confounding. Confounding, I think you guys have an understanding of what it is, but it's very important that you get that it only affects true experimental designs, where you're trying to manipulate something, where you're trying to exert control over some variable. In this case, we're exerting control over what the people are taking, ginkgo or the placebo. We're not simply looking at people already taking ginkgo versus people who are already not taking ginkgo. That would be more of a correlational thing. We don't have control over those variables, and so it's kind of inherently confounded by all the other differences between people who might take a nutritional supplement and people who don't. But in an experiment, it's a problem if these groups are different other than what you've given them to take. So anything that co-varies systematically with the independent variable, and remember that independent variable isn't ginkgo, the independent variable isn't the placebo, the variable is what they're taking, whether it's ginkgo or the placebo. That's the independent variable. It varies in two ways. You either get one thing or you get the other thing. Both of them together constitute a variable, and you can be in one group or the other. All right. Any other difference between those two groups, we say that it's something that co-varies with the independent variable. Like if we put all men in one group and all women in another, that would be a confound. And control is a way to prevent confounding. We have a potential confound without a placebo because one group would be getting to take a pill and the other group wouldn't be taking a pill. And so that's a potential confound, so we control that with a placebo. The placebo is something that doesn't do anything, right? It doesn't have any medical effect, any kind of physiological effect other than the expectation of the individual. And the ginkgo already has that because it's a pill, right? So, does it actually work? In 3510, you learned the difference between population parameters and sample statistics. Here, we're not going to give ginkgo to every single person in our population of interest, no matter what that is. We're not going to give placebos to every single person. So we're going to work with samples. So most of the statistics that we're talking about, those are statistics in its literal meaning. They apply to a sample. So we'll look at sample means, sample standard deviations, and not population parameters. Now, in a perfect world, we would sample randomly from the population of interest, but don't confuse random sampling, which has to do with the generalizability of whatever results that we happen to find, with random assignment. Here, it's random assignment that is clearly the most important thing. Random assignment assures that any differences between these groups, the ginkgo and the placebo group, before we give them the pills, any differences between those groups, they're going to be due completely to chance, and that's extremely important. That any differences before the treatment are due to chance. There can be some differences. You might have slightly more men than women in one group than another. One might be slightly more older than the other one. But those individual differences, those individual average differences between the group will be determined by chance, and it's not a systematic variation, like with all old people in one group and all young people in another group. Okay. Usually what we end up with is not true random assignment, but something called restricted random assignment, where we limit the assignment, the randomness of the assignment process, for example, to create groups of equal size. And that's what we could do in this study, and that's what we call it, so that would be fine. If we end up with systematic variation between the groups, like if we took everybody who came to participate in the experiment in the first hour and assigned them to the ginkgo group, and people in the last hour to the control group, then we would have assignment bias. That could be a problem because people who are more punctual might have a better memory or worse memory, and that could affect the outcome of the study. We could also do a matching design, but that would require different statistics. So if we gave people a memory test beforehand, which we don't need to do, but if we did, then we could match people based on their memory score at the beginning and create groups that were equivalent on the final outcome measure. So that could be an interesting strategy. But again, we wouldn't be using a between subjects statistic to analyze the data at the end. And we'll come back to matching designs when we discuss the repeated measures design. Okay, let's say that we do the study, that we're measuring some kind of memory score, like somebody suggested we measure how many numbers they could remember in a row, and we compare these two groups, the placebo control group and the ginkgo treatment group, and let's say that the scores ended up like this. On average, like 8 point some odd numbers remembered for treatment group and 6.2 something numbers for the control group. Well, did it work? It's kind of hard to say without some idea of whether this difference is meaningful. And I already know that you guys are probably familiar with the term statistically significant. And what does that actually mean? Well, that phrase, statistically significant, refers to usually a hypothesis testing statistic, and I'm going to show you how to use one in the next lecture. But remember, these let's remember what the height of these bars actually represent, all right? So these bars correspond, the height of the bars corresponds to the mean of the group that's indicated underneath. So where it says control, right? So over here it says, sorry, I keep clicking on this thing. It says control, and so the height of this bar on the left refers to the average performance of the placebo control group. Under treatment, the height of the bar refers to the mean of the ginkgo treated group. And you can see that it's higher, but is the difference between these two actually meaningful? Well, remember that these are sample means, and we'll never know exactly what the population looks like, but consider these two hypothetical populations. So this is population 1. And this is their memory score, all right? So this is the memory score of everybody that you're interested in your entire study, population 1. And not everybody has the same score. Why is that? None of these people are taking ginkgo. They're all essentially they're not even taking a placebo. They're not doing anything. This is just what their memory is like without any treatment. And the average is 8.16. Now, the lowest score that I can see here is around 6. There's a 5, but not that's only one score of 5. And the highest score is 10, so this is on a 10-point scale. The population mean here, right, the mu, and I can say mu because this is the whole population, is 8.16 with a population standard deviation of 1.18. And let's say that we randomly sampled 2 people from this group, right? And we ended up with these results. So the control group here has a mean of 6.3. The treatment group has a mean of 8.7. We have a histogram that shows that these 2 groups are pretty much separated from each other. There's not a lot of variability within each group. So the light-colored bars are a placebo-treated control, and they're clustered around this mean and fairly normal distribution. If you look at this frequency distribution where we're plotting the score on the x-axis and the frequency of these scores occurring, the number of scores in each category occurring, there's not a lot of overlap between these 2 groups. And so this is pretty compelling that it looks like ginkgo's really doing something here. And I'll come back to this idea of variability in just a moment. But consider the second population, all right? Lots more variability here. The scores go all the way down to 3. The standard deviation, even though the population mean is the same. So if you look at mu, 8.16 there. I'll go back 2 slides. 8.16 there, but in the first population we had a standard deviation of 1.18. Here we have a standard deviation of twice that, so 2.35. And if we randomly sampled from this population, right, and we ended up with the control group is actually getting 6.3, the treatment group has a mean of 8.7. Even though the means are the same, let me go back 2 slides and show you that in this first population, right, this is what the means were, 6.3 and 8.7, but the variability is low within each group, and so they separate out pretty well. Here they're not separated very well at all. There's so much overlap because even though the means are the same as in the first sort of hypothetical experiment, the variability within each one of these groups, look, they're all mixed up together. There's just too much variability here, even though the means are the same. Okay. So, I'll say again, does it work? Well, I'll tell you right now, the punchline is that in the end, we're not going to have any proof as to whether it works or not. There's no way to know for sure whether ginkgo biloba really definitely for sure improves your memory to prove it beyond a shadow of a doubt. There's always going to be some doubt. And even after we get the reports of the statistics, even after we calculate the results, we're not going to be able to say for sure. We're only going to be able to make a tentative conclusion. And I think once you see what the statistics actually do, that you'll agree with me that there's no way to know for sure. All we're really going to do with the statistic, and it is the independent measures or independent groups t-test, is it compares the difference between these 2 means. But it does so relative to the overall variability, right? So it looks at the difference between these 2 means, 8.7 and 6.3, but it takes the spread of the scores into account. And it does so simply by looking at the variability or the difference between these 2 means and dividing it by the average variability within each one of the 2 samples. All right, and it does so basically in this equation. This is a little oversimplified, but all t really is the difference between your 2 sample means. Now, I've kind of graded out here because that's not exactly all that it is. You do make that difference relative to the variability within each one of the samples. And in fact, there's even more than that because you have to take the null hypothesis into account. So the equation ends up being a little bit more extensive than just the difference between the 2 sample means. But, I mean, that really is the heart of this equation. It's how big is this difference relative to the variability within each sample. So the difference between the 2 sample means, that's kind of like saying, well, what's the variability between these two groups? And this term on the bottom, which we'll see is the estimated standard error of the difference between the two means, we're going to see is actually a measure of the variability within both of the groups. So I'm going to leave it right there and hope to see you at part 2, where we'll compute t.